Hey everyone, welcome to the third video in my alkene reaction series. Today we'll be going over halogenation reactions, which is the addition of your diatomic halogens to an alkene. Here are some definitions for you to know. An electrophile. It's an atom that is electron poor. It is an electron pair acceptor, and it carries a positive charge. Most oftentimes you'll also see that your electrophiles will be partially positive. Nucleophiles. It's an atom that is electron rich. It is an electron pair donor, and it carries a lone pair, or it can have a pi bond. Doesn't always carry a negative charge. Just like how we'll see in these reactions, your nucleophiles are alkenes. Now, other nucleophiles could also carry a partial negative charge, just like as you'll see in the double halide bond. Vicinal dihalide. It has halogens on adjacent carbons, which means that when the pi bond breaks in the alkene, your halides will attach to the adjacent carbons. Markovnikov's rule. For unsymmetrical alkenes, the electrophile in the double halide bond goes to the less substituted carbon, and the nucleophile in your double halide bond goes to the more substituted carbon for stability. So here's your general idea of the reaction. Two bonds are broken, the halide to halide bond and the pi bond in the alkene. There's going to be two sigma bonds that are going to replace the pi bond. Those are going to be your carbon to halide bonds. And for thermodynamic purposes, they're exothermic reactions, which means that the two bonds formed release more energy than the energy needed to break the pi bond. And just as a reminder, with all of these alkene reactions, they are only going to react with electrophiles. So here's your general mechanism. Let's say you have a symmetrical alkene, and you're going to react it with your halide to halide. One of these halides is going to be partially positive, while the other one's going to be partially negative. That's due to the fact that one of them is going to be closer to your alkene, which is electron rich. And remember that that's going to be your nucleophile. And it's going to create a dipole moment in this bond. Therefore, when your alkene attacks, it's going to attack the partially positive halide. The electrons will expel onto the partially negative, and it'll create a carbocation, which then the partially negative halide is going to attack and form a bond with, therefore giving you the vicinal dihalide product. Here's my question to you. Where is your electrophile? Once again, it's going to be in your halide to halide bond. It's polarized, creating a dipole moment in which one halide is partially positive and the other is partially negative. So let's look at a reaction. Let's say that we have a cyclohexene reacting to a double bromine. The pi bond is going to take the partially positive bromine, expel the electrons to the partially negative bromine, and it's going to form a bond with the partially positive bromine, leaving you with your electronegative bromine. During this reaction, something interesting occurs. The bromine that's already attached to your cyclohexane is going to resonate between that positive carbocation and the carbon that it was bonded to, forming a bromonium ion. So with this bromonium ion, bromine is going to attach itself to both carbons. It will carry a positive charge, and your carbons are going to have a partially positive charge. This is due to the fact that bromine still has a strong pull on its electrons that are attached to carbon. Therefore, they're going to be closer to bromine than they are to the actual carbons. Now, your electronegative bromine is going to attack one of the carbons In this case, it doesn't matter which one because your molecule is symmetrical. It's going to perform a backside attack and attach itself to said carbon. Forming this halonium ion prevents any carbocation rearrangements from occurring, and it allows for the halide to bond to the adjacent carbon. But now, what happens if we have unsymmetrical alkenes? Well, Markovnikov's rule comes into play with this. So let's look at an example here. Let's say this double bond takes your partially positive bromine. The bond between both bromines is going to break, and the electrons will expel into the partially negative bromine, and it'll form your bromonium ion. Now, let's take a look at the structure. One of the carbons is a tertiary carbon. The other is a primary carbon. Which one do you think the electronegative bromine is going to attack? It will be the more substituted carbon due to the fact that it's going to create a stabilization. Therefore, you come out with this product. And Markovnikov's rule will stand. Only the most stabilized carbocation will form when it comes to adding your diatomic halide. What if you have an electronegative atom in your alkene? This is when you have to start thinking about resonance. And due to resonance stabilization, your more electronegative atom in your halide to halide bond will attach to the carbon close to the electronegative atom. So let's take a look at an example. Let's say that you have this cyclohexene with an oxygen in the ring, and you're going to react it with this bromine to chlorine bond. Being said, chlorine is your more electronegative atom, therefore it'll carry the partial and negative charge, and your bromine is going to be the partial positive atom. So your pi bond is going to take the bromine, expel the electrons to chlorine, and it's going to form a bond. So now the question is, which carbon is going to take bromine? For that reason, we'll look at the way that this molecule resonates. Let's expel a lone pair from oxygen to make a double bond between the oxygen and the adjacent carbon. Let's expel the pi electrons onto this carbon to give it a lone pair and to give oxygen a positive charge. So now this bond is too strong to be broken at the moment. This carbon atom is going to take bromine. It's going to break the bond between bromine and chlorine, expel the electrons onto chlorine, giving you the carbon to bromine bond. Now, the pi electrons in carbon are going to go back to oxygen because oxygen is not happy with its positive charge. And it's going to form a primary carbocation. Bromine is going to want to resonate in between these carbons, forming a bromonium ion. And then chlorine is going to do a backside attack and form a bond with the adjacent carbon, giving you this product. Take note that your chlorine is attached to this carbon due to the fact that it is more electronegative since it is right next to an electronegative atom. Know that you can be tested upon this reaction with aprotic solvents included, such as CH2Cl2, CCl4, or CHCl3. If you see this paired with your reactant as a double halide, know that this is going to be a halogenation reaction. So let's move on to the stereochemistry of this reaction. The enantiomers that will be formed from this reaction will be trans products, meaning that your halides will attack from different sides. So why do trans products form? This is due to the fact that your halonium ion forms, and the steric effect that it contains will hinder your electronegative halogen from attacking on the same side. So just as a summary, when the alkene attacks the halogens, a halonium ion is formed. The first bond occurs on one side. It could be front or back. And because the halogen ion blocks the second attack on the same side, the second attack must occur on the opposite side. It is an anti-addition reaction. Now, let's take a look at some examples. So in this example, you have a symmetrical alkene reacting with a diatomic bromine atom. The pi bond is going to attack the partially positive bromine, breaking the bond between your two bromine atoms and expelling the electrons back to your partially negative bromine. This attack will occur on the front, therefore your halonium ion will occur on the front. And then your electronegative bromine is going to attack one of the carbons, expelling the electrons in the bond back to bromine and giving you a trans product. Now, you can also have the attack occur from the left side as well, which can also give you the other enantiomer. Let's take a look at the next problem. Here you have an unsymmetrical alkene reacting with a diatomic chlorine atom. Your pi bond is going to attack the partially positive chlorine, breaking the bond between your two chlorine atoms and expelling the electrons back to your partially negative chlorine. This in turn forms a halonium ion, and since this halonium ion was formed on the front, your negative chlorine atom is going to want to attack from the back. Now, it has a choice between two carbons, a tertiary one or a secondary one. Your electronegative chlorine is going to want to attack the tertiary due to Markovnikov's rule and reasons for stabilization. So you will have this product form. Now, you can't have the other one form because of the fact that Markovnikov's rule states that the more substituted carbon will get the electronegative atom, and this just isn't stable. So you can just ignore this. Let's look at the next example. The only difference between this example and the previous ones that we have done is the fact that I've added CCl4 as a solvent. Don't be afraid whenever you see this or any of the other aprotic solvents I've mentioned in the video. Just know that it will proceed as a halogenation reaction. So now your pi bond is going to attack the partially positive bromine. It will break the bromine to bromine bond, expelling the electrons back to your partially negative bromine. And in turn, you'll have a bromonium ion form. Now, the electronegative bromine has a choice between a tertiary carbon or a secondary one. Your bromine is going to attack the tertiary one because of Markovnikov's rule, and the carbon to bromine bond in the bromonium ion will break. The electrons will go back to that bromine and give you this as a product. So that is it for my video. If you guys have any other suggestions or want me to make any other videos on mechanism, just let me know in the comments below. Don't forget to subscribe and give this video a thumbs up.